This is video number 19 on Probability for Actuarial Exam 1, also called Exam P. In the first 18 videos, we've done problems that you can find on the Society of Actuaries website online that are practice problems for that exam. And the last couple of videos, I talked about examples that involve discrete random variables. But I found that there's not really a ton of those examples online, so instead what I'm going to do on this video, and probably in a number of videos to come here, is do some modified versions of problems from this book, Probability and Statistics, a problem-solving text by Leonard Asimov and Mark Maxwell. This was published back in 2010. I think there's got updated versions here. But again, I'm modifying the problems. We need this kind of background to more fully understand other stuff. So I think it's definitely worth doing. So it's good knowledge to have if you want to be an actuary or if you just want to understand probability. So we'll be finding and graphing a probability mass function. Again, we talked about that in the last couple of videos, PMF, and something new, a cumulative distribution function, CDF, for these things called discrete random variables. In this case, the discrete random variable gives the number of heads when flipping an unfair coin, a weighted coin, not fair, 3 times. Usually you flip a coin that's fair that has a probability of heads of 0.5, 50% on any given flip. This time it's going to be 60% is your probability of heads on any given flip. You could also think of this video as being an introduction to binomial random variables, a special kind of discrete random variable. We'll talk a lot more about binomial random variables in videos to come. So again, it's a modified version of exercise 3.7, 3-7. A loaded, in other words, unfair coin has the probability of heads equal to 0.6, 60% on any individual flip. However, our random experiment is to flip the coin 3 times and count the number of heads. The random variable x represents the number of heads. Think about that. In 3 flips, you could have 0 heads, you could have 1 head, 2 heads, or 3 heads. There's 4 possibilities for x. Part A, I want to find the probability mass function, PMF of x, find, in a sense, well, its values, maybe even a formula for it. Part B, find the cumulative distribution function. This is something new, also called the CDF of x. Part C, we want to graph these functions, the PMF and the CDF. I will say that in graphing them, I want to take a different perspective than I've done so far. We focused on these things being discrete and therefore thinking about the graph only at whole number values of x. However, for the general theory, it's actually best to think about x even being any real number, okay? Though that we'll have to be careful when we make the graph in that way. I also should note there's an implicit, in other words, unstated assumption that we have to make to solve this problem. You might want to pause the video and think about what that implicit, unstated assumption would be. All right, we can start by listing out the sample space of possible ways, things that could occur, outcomes, when you flip a coin 3 times. However, because it's an unfair coin, you should realize that in so doing, the outcomes, the individual outcomes, are not equally likely, so you cannot use the simpler approach of just counting outcomes. You could get 3 tails, TTT. You could get 1 head and 2 tails, but that can occur in 3 different ways: HTT, THT, and TTH. You could also get 2 heads and 1 tail, and that could occur in 3 different ways, like this. Or you could get all heads. That's the sample space for this experiment based on thinking in terms of the outcomes of each flip. We can relate this to this random variable x, and it is a discrete random variable. It can only take on, in this case, finitely many values. Discrete random variables either take on finitely many values or what's called a countable infinite number of values. More on what that means in later videos. This outcome, where you get all tails, corresponds to x equaling 0. Right? X is the number of heads. There are no heads there. These 3 outcomes correspond to x equaling 1. These 3 outcomes correspond to x equaling 2. And this single outcome corresponds to x equaling 3. But again, these are not equally likely. So for example, the probability that x equals 3 is not 1/8. It's going to be higher than 1/8 because this is higher than 0.5. Likewise, the probability that x is 0 is going to be less than 1/8 because the probability of tails on any individual flip would be 0.4. Let's go ahead and calculate these probabilities now, one at a time. The probability, first of all, that x equals 0 is going to be, think about it here, the probability that you get 3 tails. And here's where the implicit, in other words, unstated assumption comes in. You need to assume these individual flip outcomes are independent of each other, unrelated. The outcome of any one flip does not affect the outcome of the next flip. The coin does not have a memory. That's not stated in the problem, but it's a natural assumption to make, and it's really an assumption you have to make if you're going to finish the problem. So I can use the special multiplication rule for independent events to say it's the probability of tails in the first times the probability of tails in the second times the probability of tails in the third. All of those are 0.4. 1 minus 0.6. So you're going to get 0.4 cubed here. 0.4 cubed is 0.064. Yes, and that is less than 1/8. Okay, like I mentioned before. How about the probability that x equals 1? We also need here the special addition rule for mutually exclusive events. These individual events are mutually exclusive. You know, that's not stated in the problem either, but that's definitely something that is obviously true. It's not really an assumption you need to make. These individual outcomes, HTT, THT, and TTH, cannot simultaneously occur on any one run of the experiment. So this would be the sum of their individual probabilities. That is the special addition rule for mutually exclusive or disjoint events. Then for each of these, you use the assumption of independence to multiply the probability of heads times the probability of tails times the probability of tails. And then with this one, multiply the probability of tails times the probability of heads times the probability of tails, etc. And multiplication is commutative. It doesn't matter what order you do those in. All three of these are going to be the same number. And the answer is going to be 3 times, think about it, 0.6 times 0.4 squared, right? Because the probability of heads on any given flip is 0.6. The probability of tails on any given flip is 0.4. You've got 2 tails in each case, so you have to square that. And again, these are all the same number, 0.6 times 0.4 squared, so you have 3 of them. You've got to multiply by 3. 0.4 squared is 0.16 times 0.6 times 3 is 0.288. Okay? On to the probability that x equals 2. I'm not going to write it all out. Think about the analogy here. You're going to get 3 times, well, now heads is occurring twice. You're going to get 0.6 squared, and tails is only occurring once. You're going to get a 0.4 to the first. 0.6 squared is 0.36 times 0.4 is this, times 3 is 0.432. Finally, the probability that x equals 3, getting all 3 heads is 0.6 to the third power. It only occurs in one way. 0.6 to the third power is 0.216. Okay, now what you should do now is you should check this by adding these numbers and seeing if you get 1. If you don't get 1, then you did something wrong, unless you did some rounding. 0.064 plus 0.288 plus 0.432 plus 0.216 does equal 1. Okay, that's not a guarantee that we haven't made a mistake, but if we did not get 1, then we definitely had made a mistake. All right, can this be generalized? Can we talk about the probability that x equals k, where k is one of these 4 numbers, 0, 1, 2, or 3 in this example? You can. Let's leave the, the coefficient blank for the moment. In each case, the 0.6 really gets raised to the k power. Here there's really like a 0.6 to the 0 power, because that's a 0. Here there's a 0.6 to the first power, that's a 1. Here 0.6 squared, that's a 2. 0.6 cubed, that's a 3. You'd put a 0.6 to the k power. The 0.4 gets raised, really, if you think about it, to the 3 minus k power. What goes in front? Well, the pattern is 1, 3, 3, 1. Is there a way to represent that in terms of 3 and k? It turns out there is. It's 3 choose k, sometimes written like that, sometimes also written like this, 3ck. It's called a combination. Maybe you've learned about combinations before. They involve, the formula for it involves factorials. If you've never heard about it before, that's okay. I'll talk about it in later videos. If you have, you might want to check that this does work, where k is 0, 1, 2, or 3. All right, let's go on to making a table of values for this PMF and then talk about the CDF. And then we'll make a graph, and then we'll use Mathematica to talk about the binomial random variables in general and make animated graphs. It'll be kind of cool. So for this case, little x are the different values that capital X can be. Remember, the capital letters refer to the random variables themselves. The lowercase letters refer to their values, particular numbers that they can be. It's more like a variable, a regular variable. In the last couple of videos, the PMF I denoted by little p for the function name. Here I'm going to denote it by little f. It's common to use little f as well. Little f of x represents the probability that capital X equals the given little x. I used little k in previous videos instead of little x. This is the PMF, and its values at 0, 1, 2, and 3 are the values that we found here, these 4 numbers here. Just transfer those numbers over to this table, 0.064, 0.288, 0.432, and 0.216. And again, those add to 1. The CDF, cumulative distribution function, accumulates these probabilities. That's why it's called the cumulative distribution function. It's commonly denoted by a capital letter, capital F in this case, of little x. It is the probability of capital X being less than or equal to the given little x's. Okay, so again, little x is the variable for this function. So when little x is 0, what is the probability that capital X is less than or equal to 0? Well, it can't be negative, so it's the same as the probability that it equals 0. That's a special thing that happens with discrete random variables. It doesn't really happen with continuous random variables. What about when little x is 1? What is the probability that capital X is less than or equal to 1? The only way that could happen is if capital X is 0 or capital X is 1. Those are two mutually exclusive events. You add those probabilities. 0.064 plus 0.288. 0.352, that is the value of capital F when little x is 1. When little x is 2, what is the probability that capital X is less than or equal to 2? That means capital X is 0, 1, or 2. So you add these three by the special addition rule for mutually exclusive events. So I can take the previous 0.352 and add on the 0.432 to get 0.784. And finally, when little x is 3, add on the 0.216 to confirm we get 1.000. Okay, so that's the values of the CDF. You could come up with a formula for it essentially by adding these things, putting a summation sign in there. It's not really necessary to do here. I'm going to graph these things now. And again, in the graph, I'm going to pretend these functions are defined for all real little x instead of just these whole number values. That is, in general, a good idea for reasons I'm not going to get into in this video. So here we're going to graph the PMF. Value, I'm going to make a scale here, maybe 0.1, 0.2, 0.3, 0.4, and 0.5. And here's the values of little x. This is the graph of little f of x. Its value when little x is 0 is 0.064, so right about here. Its value when little x is 1 is 0.288, so that would be right around here. Its value when little x is 2 is 0.432, right about here. And its value when little x is 3 is 0.216, right about like this. Of course, this is not perfect. You could try to do a better job than me. If this is going to be defined for all little x, all real little x, what are its values at other values of x, like 0.4 or pi or something like that? It would have to be 0. That would be the only thing that would make sense. The probability of any of those other values is 0. So what I can do is I can make open circles at 0, 1, 2, and 3, and then just make a horizontal line in between those open circles The open circles just emphasize those points are not part of the graph. Okay? So it seems really weird to do that, but that actually is something that is done and is a good idea for certain reasons. Again, I'll get into later in later videos. How about the CDF graph? So now we're graphing capital F of x, and its highest value that it gets up to is 1 here. There's 1, here's 0.5, 0.25, 0.75, say. Here's 0, 1, 2, and 3. Its values at 0, 1, 2, and 3 are these numbers that you see here. 0.064 down here when x is 0. 0.352 when x is 1. That gets up to about, let's see, maybe it'd be about right here or so. 0.784, it jumps up to way up here when x is 2. And finally, when x is 3, it jumps up to 1. What should we do if we're going to draw this for all real values of little x, however? It's not going to equal 0 for those other values of x. For example, what is the probability of capital X being less than or equal to, say, 1.4? It can't equal anything between 1 and 1.4. That is the same as the probability that it's less than or equal to 1. So its value at 1.4 is the same as its value at 1. It's the 0.288. In fact, it's got to be a horizontal line in here, and down here, and here, and here. How far does the horizontal line go to? Here it goes to this point that's missing, not part of the graph. Here it would go to this one. Likewise, on this one, it would go up to this point right there. Again, open circles means the point is not part of the graph. And it would go on forever in that direction, and I guess back when x is negative, it could be defined as well, and it would make sense to equal 0 over there. So that would be how you graph capital F of x as a step function, a discontinuous step function for all little x. And again, this can be a good idea in general, as we will talk about eventually. Let's end the video by looking at Mathematica. And again, what I want to do with the Mathematica is make some graphs that show you the behavior of binomial random variables in general. At least when you're, it's like when you're flipping a coin 3 times. You could flip more than 3 times if you want as well. But essentially, by doing this code right here, I'm defining the PMF, although Mathematica calls it a PDF for probability density function, but it's really better to call it a PMF for the discrete case. The PDF really stands for the continuous case as a better name, but Mathematica uses PDF. Binomial distribution, the 3 represents the fact that there's 3 flips. The P represents the probability of getting heads on any given flip, which was 0.6 for the problem. And the X is going to be the variable for this function. And here's the CDF. So this code will enter these functions. I can make a table of values for the PDF when P is 3/5, and I can write the answers in terms of fractions. There they are in terms of fractions. We got numerical, well, decimal approximations to these, like you see here. I use this capital N function to see those. Here, Mathematica is programmed to find the values of this function for other values of x besides those between 0 and 3. It's assumed, by the way, with this table command that x would be 0, then 1, then 2, then 3. So I'm going from -2 to 8 here, and you see you get a bunch of zeros when x is -2 or -1 or 4 or 5 or 6 or 7 or 8. If you want to get more decimal places, you can add on this extra comma 20 there. I went back to going from 0 to 3 here, but that's not necessary in this problem. Here's a way to display the data nicely for the PDF in this case, and in terms of fractions, you could double check that these fractions all add to 1. This summation will confirm the sum of these things as 1. That would include even if you let x go from -2 to 8, or in fact, if you let x go from -infinity to infinity. Actually, this is one of the reasons why it's a good idea in general to allow it to be for all x, because it makes definitions easier to state. Some important definitions related to summations in probability. Here is a plot, as Mathematica makes the plot, with vertical lines. Technically speaking, those vertical lines are not part of the graph. This is when P is 0.6. I tried to use an exclusions thing to make sort of open circles along the axis at 0, 1, 2, and 3. It doesn't do it here when it's static, but when I move the slider, you can see there's a little bit of space. in the red spot along the horizontal axis at 0, 1, 2, or 3. Do you see that? Little spaces in there indicating those points are missing. And also the vertical lines go away. That's kind of nice when I have different values of p. When the probability of heads on any given flip is very high, you have a very large chance of getting 3 heads. That last dot up there is very high. When the probability is low, you have a very large chance of getting 0 heads. Again, the ordinary fair coin situation is when the probability of heads is 0.5. This is what you would get. And again, our problem is 0.6, and you can check that these values are the values of the PDF, like I graphed by hand. The CDF can be graphed as well as a step function, in fact. And here's what it looks like when p is 0.6. This is like the one I drew by hand. When p is large, the graph looks like this, indicating that you are highly likely to get close to x equals 3. Because, for example, the probability that x is less than or equal to 0 or 1 or 2 are very low. On the other hand, when p is low, the graph looks more like this. Okay, it's always going to be a step function. Finally, you can put these graphs together in a picture that looks like this and compare them. And if you think about this, for any one of these values of p, which again represents the probability of heads on any given flip, it's almost like the little f, the red graph, is a derivative of big F. In fact, that definitely would be true as long as little x is not a whole number, not an integer. The slope of the blue graph is 0 when x is not an integer. It's undefined when x is an integer, so I guess the values of little f are not quite the derivative of capital F for those values, but the heights of these functions would essentially give you the amount of increase in the step function. So for example, the height here at 1, which is close to 0.45, is the jump at 1 in this graph. So it's almost like little f is a derivative for capital F, and that's going to happen definitely in the case where you have continuous random variables. Thanks for watching.